Hey everybody, my name is Brian Metzger. I am an application engineer here at Trimex Solutions, and my main focus, what I spend most of my time on, is the simulation products in SOLIDWORKS. Today we're going to be taking a look at SOLIDWORKS Simulation, which is our finite element analysis package. It's going to look at stresses and strains in solid bodies to see if your parts are strong enough to hold the loads that you intend them to. Today's goals are going to be to give you a basic introduction to FEA simulation in SOLIDWORKS. We want to give you an overview of the simulation tool set, and it's impossible to do every single thing that we can do. We're going to focus on three key areas. We're going to look at the basic linear static studies, we're going to run an optimization, and then we're going to check with a frequency study to see those fundamental modes of vibration. Finally, we're going to come back and talk about what does it all mean, what's the point of it all. So let's take a step back. Let's think about how things are done before we had simulation available to us. We'd probably start with a basic conceptual design, maybe a napkin sketch. Maybe you and your team are getting together on a whiteboard and hashing through some ideas. And then you've got to go and do a detailed design. You've got to work out how things are going to go together, where the bolts go, how things are going to be cut, all the details. And most of us that have been doing this a while hopefully are already working in SOLIDWORKS. We're already doing this design in the most powerful parametric modeling package that's available to us. Now, you got to check to see if it's good enough, right? So usually that means fabricating a prototype. You've got to do that so that you can do a functional test and see if something's going to break, if things are going to bump into each other, if something's going to bend farther than you want it to. You got to test that out in the real world because you just don't know already. If you fail that bench test, if it's not good enough, you got to sharpen your pencil and go back to the drawing board. Start over again, redesign, refabricate a second prototype, and keep going around, looping through this cycle as many times as necessary so that you can get to a final product that you can monetize. And how do we validate a design, right? Either before we've tested it or after. We've got a number of different tools at our disposal, right? We've got our intuition as engineers. We're all very smart. We can look at that and our experience from all our years designing things within whatever industry we're working in. And we can try and think, we're pretty smart people. We know what's going to work, right? We hear this all the time when we go out and talk to companies about simulation. We just know what works, right? You can base it on a previous design. You can say, this is what we did last year. It didn't break, so let's do something similar. Let's start from that and just modify it. And SOLIDWORKS is great for this, doing derivative designs, right? You can talk to your vendors and find out how big things are going to be. Things like how strong a bracket needs to be to hold up a certain piece of equipment, how to size a motor for a certain load. This happens all the time, and vendors are happy to give their recommendation. I used to get a story told to me from one of my professors in college, though. He said, if you're looking for a recipe and you call up the pepper company and you ask for a recipe, they're going to give you a recipe that uses a lot of pepper, right? So you're taking the trust in your vendors in hand here. Another thing we see all the time, over design, right? When in doubt, build it stout. We don't care if something's way too heavy or if we spend an extra couple of dollars to make it. We're going to make it just way stronger than it needs to be just to be absolutely sure. And, maybe that's okay, I guess. And finally, if we really need to know what's going on, we prototype and test, and then prototype again and test, and just keep going in that cycle, repeat, as many times as necessary. And what we'd like to shift to in the new paradigm is doing even more of that, but using simulation, we can prototype and test very quickly and at a very minimum cost, because we're not paying for our machine shop hours. We're not paying for material. We're not adding an incredible amount of time to our schedule, waiting for quotes back from the shop, waiting for fabrication, running a long test. We can just do it on the computer screen, sometimes in minutes or seconds, and go through a very large number of ideas before we get to our final design. So it's not just about the cost of these prototypes in dollars. It's all about the schedule. When you use design simulation in the software side, you can compress your schedule by putting some of these activities on top of each other, giving you a faster time to market. And that's a big deal for a design company. And of course, it's always painful when something doesn't work, right? We can do as much checking as we can. We can try to really test things for strength. But in this example, we've got a helicopter. It's been tested for strength. It's been tested for flight hours, but something wasn't taken into account. Probably a frequency analysis wasn't performed to see that some of the structural integrity of this would vibrate at a fundamental frequency that matched the motors in the helicopter. And it does not go well, right? Even if this is budgeted into your schedule, a result like this is painful. We don't want to be responsible for something like this happening, right? So what is design simulation? What are we talking about? We're going to try and do product performance at the same time as we're doing the design, right on top of each other. We're going to try and get rid of all that costly redesign, all that when in doubt, build it stout, things that are 10 times stronger than they need to be, 10 times more material than they need to have, 10 times heavier than they need to be, and we're going to get to market faster. We've got a variety of different products, and today we're just going to be focusing on the structural simulation, but SOLIDWORKS also has solutions for rigid body motion simulation, for moving jointed mechanisms. We've got a fluid dynamics and heat transfer package. We can look at environmental impacts, and we can look at MultiPhysics. Today we're going to use the example of Resimon. Now Resimon is a really cool company out of South America. They make equipment for the mining industry, and we're going to be looking at this piece of equipment, the Bolter 77D. This is a piece of equipment that is used to go into a mine shaft and reinforce the walls of the mine that have just been drilled out for mechanical rock support. So what we're seeing here is the vehicle has to be nimble enough to get into the mine, maneuver around, and then these big articulated arms are going to pick up a piece of wire mesh, hold it up to the wall of the mine, and then a second arm is going to both drill a big hole in the wall of the mine and then insert a giant threaded bolt into the wall to hold up that mesh. Now that mesh on its own can protect from falling rock, or sometimes if they really want to improve the stability of the mine, they can spray it with concrete to hold everything up. You see the bolt being placed in here, held with a claw, and then let go as it's finally finished. This is a really amazing piece of equipment, and everything moves on it. Everything has to move around because they have to make it their way through this kind of curvy mine path and back out again. So things have to be very, very strong, but it's also important for parts to be light so that all these jointed mechanisms that hold them up won't be prone to failure by any possible way, right? So this is a very complex piece of equipment with thousands of parts, all designed in SOLIDWORKS. We're going to take a narrow approach today. We're just going to focus on one little piece of the design. We're going to look at one of the knuckles that holds up the hydraulic cylinders that lift and lower that boom arm. This is a critical piece of equipment. Think about it. All that design, all the equipment on this whole rig is all for nothing if one of those knuckles fails, right? The whole thing comes crashing down. So I've got my model of this boom knuckle from the Resimon bolter. We're going to just test it in a simple static study to see if it's strong enough to hold the expected loads. I'm going to do this in SOLIDWORKS by simply asking for a new study, and I'm going to pick my study type. Linear static is the simplest, most basic kind that we can do. So I've got a number of things I need to define in a static study. First of all, I have to give materials to all of my parts. Sometimes you've got multiple parts with different materials. Here, I'm going to go into my material database. I'm going to make them all the same just for simplicity's sake. I'm going to make these all 1020 steel. Now when I define the materials, what I'm defining are all the material properties, how this material responds to changes in the stresses, right? And the four important properties that I need for a linear static study are the elastic modulus, Poisson's ratio, the density, and the yield strength. Now, if you're not doing simulation, if you're just modeling in SOLIDWORKS, density is the only one of these you ever use. It's how you get the masses on your parts and assemblies. So I'm going to apply those and close out my material catalog. Next, I need to define how things are connected together, right? I could have pieces that slide against each other, pieces that are pinned together, and when I start a linear static study with more than one body in the assembly, I end up automatically getting a global bonded contact. This is the most basic way we can do things. It's going to simply bond together any pairs of surfaces that have face-to-face coincident contact. This is good enough for right now. It's going to give us a good first look for demonstration's sake. It's going to treat everything as if it's glued or welded together. Not a perfect example of how this bolter is really going to work, but we'll stick with it for right now. Next, I need to define how things are held in place. I'm going to use fixtures. So I'm going to define a fixed geometry on the two faces of the bolter pin where it's going to be attached to the next piece of the assembly that's not included here. All of the points of calculation on those cylindrical faces are going to be held still when I go to calculate. I'm going to put in an additional one just to show an example of something else you can do. I've got these wear plates on the top and bottom. And on those, I'm going to define a roller slider contact. That's going to mean that they're not allowed to move in and out of plane, but they can slide around on the plane of contact. And notice you get these great little animations that kind of give you an idea of what each type is going to do. Awesome. So next I need to define my loads. This is another kind of boundary condition. I'm going to simply put a force of 180,000 newtons on the pin where my cylinder is going to be attached. That is the capacity of the hydraulic cylinder that's going to be lifting and lowering the boom arm. So this is all very simple and intuitive so far, right? The next step gets slightly abstract, but not too bad, right? So I've got to calculate what's going on in all of this material by breaking it down into a large number of small pieces, and that's going to be called a mesh. When I go to create my mesh, it's actually going to break down the entire volume of all of my solid bodies into small tetrahedral elements. Now I've got a slider bar from coarse to fine, and that defines whether I get a large number of very small elements or a smaller number of larger elements. There's an inherent trade-off here. If I have smaller elements, I'm going to tend to get more accurate results, and that's a great thing. We always want that, but I'm going to have more of them, so it's going to take longer to calculate. So there's always a trade-off. Here, kind of a medium density mesh is good enough. And let's take a mesh plot here so that I can show you just how this looks through the middle. It's kind of cool. We're actually getting three-dimensional elements all the way through the thickness. And we can use mesh sectioning to see that. Notice how we get these three-dimensional triangles all the way through as I drag the plane through my part. Really, really cool. Alright, so I've got a mesh. If I take a look at my details here, I've got 70,000 nodes, about 200,000 points of calculation. That means that with the boundary conditions that I've applied and with the mesh that the computer has given me, what needs to be done in order to solve this problem, to get a result, is to solve 200,000 equations with 200,000 unknowns. Now that would be very, very difficult for me, but lucky for me, solving a large amount of equations is exactly what computers are good for. This is only going to take a couple of seconds for my CPU to crunch through all of those calculations and give me a result. And we start out looking at our stress plot. Now the first thing you notice about this is that the material looks like it's bending. It's showing me how the material is going to sag. And it looks pretty bad. It's moving a good distance. And this freaks people out sometimes because what we're getting here is an exaggeration of the displacements that are being calculated on the part. I can show a displacement plot where the colors are corresponding to how far each node in the mesh is moving in this simulation, and we see off to the right of the screen that my maximum displacement is about 1/4 of a millimeter. Not terribly bad, but if I showed these to scale on the screen, it would look just normal to me. And that's a property of these linear static studies. One of my assumptions is that I'm getting relatively small displacements compared to the size of the part. So in order to get a intuitive look at what's going on, which way things are moving, and what kinds of deformations we're seeing, the computer exaggerates the scale on the screen for us. Back to that stress plot. We can show the maximum stress, which turns out to be down where the pin attaches to the knuckle. That makes sense. That's kind of a sharp corner. We also see concentrations on the inside radius of the knuckle. That's also to be expected. Now, my yield strength here is about 350 megapascals, which it turns out to be, what, 351 million pascals? And I'm not quite hitting that, right? I'm hitting maybe a third of that, which means that my knuckle is over-designed a little bit. It could be stronger, but I could make it a little bit lighter and still get away with it. Now, depending on the application, you might want to design to a higher factor of safety. You might want to design something to be twice as strong as it needs to be, just as long as you're not making it 50 times stronger and way too heavy. A good way to look at this, especially when I've got multiple different parts with different materials associated with them, would be to create a factor of safety plot. What this is going to do is normalize everything by the yield strength and show me the areas that are closest to failure. So I have a minimum factor of safety of about 1.4. That's pretty good. For an important application like this, I probably actually want it to be a little bit stronger. I probably want to shoot for maybe a factor of safety of 2, right? I want to make sure that I absolutely know this is not going to fail. So this is a good test to do. Back to the stress plot, I can look all over the place for different stresses, and if I want to know the exact stress at a particular point, other than the maximum, I can use a probe tool. Simply pick points around a corner, and if I organize my screen a little bit, I can see exactly what those stresses are read out to me or plotted. Really powerful tool. Problem is, so far I'm only looking at the outside of all of my bodies, right? I'm limited to the outside faces. What if I want to look inside the thickness and see what's going on? For that, I can use a section clipping to slice the part in half, and I can drag this in and out of the part looking for areas of higher or lower stress in the middle. Now that's really hugely useful a lot of the time, but if I want to really hone in on high stress areas, what I would use is the ISO clipping. What the ISO clipping does, instead of showing me stresses that are on one side or the other of a plane, it's hiding or showing stresses that are above or below a particular value. So I can look through my part and see which pieces of material are very close to failure, and also I might want to see which areas of the part are not doing a whole lot of work, where I could maybe stand to thin out the material a little bit, right? Maybe these arms could be a little bit skinnier for what they're doing, since really it's just the material at the corners that's doing most of the work. This could inform me to either add or subtract material to make a more efficient, better design. Okay, so I've got my stress plot. I've done all this work. What now, right? It looks great, but what's the point of all this? I know that it's good, but not quite good enough, but it's given me some insight into how to make changes. And this is where we get into one of the main benefits of using SOLIDWORKS simulation, is that we're working inside the SOLIDWORKS interface. Everything we've done, we didn't have to export out into a separate program, make a bunch of changes, and then if we want to do another simulation on something similar, we've got to start over and do all that work again. This has all been kept inside of SOLIDWORKS. So if I want to make a change, like maybe beef up this radius to make it a little bit stronger, I can do that very easily. I can come back over into my model, make a change to a dimension, make this 20, and I come back over into my study, and everything's ready to go. I haven't changed any faces that I've placed boundary conditions on. My setup is still valid. My mesh and my results need to be updated, but all I have to do is hit run again. And I'm going to get another iteration of the study on that same design. So now when I evaluate this new design, I see that I've reduced the stress in that corner and made the whole thing just a little bit stronger. I've got a new maximum in a slightly different place, but that's okay. And I can keep on going through and making changes over and over and over to this part to see how to make it the best possible design it can be. And that's really, really powerful, that in a couple of hours I can go through maybe dozens or even hundreds of different iterations on this part. Very, very cool. So I've gone through, I've made a couple of changes maybe, I've gone back and forth on a couple of dimensions, but I want to make sure that this is the best possible design it can be. I want to optimize it using a design study with the optimization option here. This is going to allow me to run through a whole bunch of different dimensions and find out which one's going to be the best for my goal of making this part use the least material possible, right? Because I want it to be lightweight. I also want it to be cheaper to make because I'm going to be making a lot of them. I've already got some variables set up here. So I've got both the thickness of the arm set up as the variable and the radius that I was changing before. Now I can range these up and down between certain values. Now I'm going to set my own maximum and minimum on the range within which I want this optimization to stay. So I'm going to say I want the arm to be somewhere between 20 millimeters and 30 millimeters, and I want to keep that radius somewhere between 10 and 30 millimeters. By giving it these bounds, it's going to try multiple simulations over and over and over again, checking different combinations of different staggered dimensions on all of these variables, right? And it's going to track the results. Now I need to also give it some constraints, things that I want to be tracked. So I'm going to add some simulation sensors. I'm going to look for simulation data which is going to count as a failure point. If I go over or under a certain value, then I don't want that iteration to be used for the optimization. And the easiest thing to use here is that factor of safety, right? I want to look for the minimum factor of safety, and I want to make sure that it is greater than 1.4 on my static study. Well, we'll say 1.5. Let's see how that goes. And I'll give it another one. I want this bracket to be stiff, so I'm also going to track the displacement. I'll use the resultant displacement, which is the resultant of the x, y, and z displacement vectors. And I'll say that I want nothing more than a 1/4 millimeter of movement. I'm going to range through different combinations of arm thicknesses and radiuses, anywhere between 20 and 30 millimeters on the thickness, between 10 and 30 millimeters on the radius. It's going to try different combinations of staggered dimensions. It's going to rerun the simulation each time. It's going to reject any version with a factor of safety less than 1.5 or a displacement greater than 1/4 millimeter. And of the ones that remain, I want to give it a goal to seek. And all I'm going to do here is add a sensor for the mass of the entire assembly. And I want to minimize that mass. It's going to try to give me the version of this boom knuckle with the lowest mass that still passes those tests. Okay, so we just finished this up. I've actually run through 9 different iterations of this simulation. It used 3 different measurements on the arm thickness, 3 different measurements on the radius, and did a simulation for every possible combination of those 2 dimensions. Going through, iterations 2, 4, 6, and 7 all failed for either having a minimum factor of safety below 1.5 or a maximum displacement above 1/4 millimeter. Of the remaining iterations, it's going to look at those dimensions, interpolate between them, and give me this optimal measurements, which it's actually brought back into my model so that I have now the best possible boom knuckle that can be designed on those measurements. Now I could do more of this, I could change other dimensions, I can set up lots and lots and lots of them, let it go overnight when I go home, or maybe go out to lunch for an hour, and when I come back, I've got my design done for me. This is really, really powerful. Now there might be just a little bit more checking we want to do. I'm going to check one more thing because we saw that helicopter fall apart because of resonant frequencies. We want to check for that. All solid assemblies are going to have some resonant frequency at which they tend to like to vibrate, and they will shake themselves to death. So we want to watch out for this. If you've ever seen the video of the Tacoma Narrows Bridge, this is what I'm talking about. So another thing we can do in simulation is we can run a frequency study. This is really cool stuff. What the frequency study is going to do is measure those natural modes of vibration. Now, I've already done a lot of the work for setup. I've already done all these material definitions, boundary conditions, the mesh, so I can actually steal all of that from my linear static study. I'm going to grab the parts folder, which has all of my materials, and the fixtures, and bring them over into my frequency study so that I don't have to redo that work. I could do it with or without the force, but right now I'll do it unloaded just to see what the basic frequencies of this part are going to be. This is kind of a worst case scenario right now. If I look into my properties, I can calculate for any number of fundamental frequencies. I'm just going to do the first 5 in this example. Again, it's going to mesh automatically when I hit run. So let's just take a look and see what our results look like. Okay, so I get kind of a weird plot. I get the resultant amplitude plot. It's not entirely obvious what that is. What I'm getting here is a mode shape. It's the type of vibration that I should expect under the first resonant frequency. And the best way to look at these is to animate them and to see, in this case, my most likely mode of vibration is going to be side to side. Taking a look at the second one, my second mode of vibration is going to be up and down. Third one is going to be more of a twisting vibration, rotating around the x-axis. This gives me a sense of where my mechanical instabilities are. I can also look at a chart of all of those resonant frequencies. This is what I want to look out for when I start designing the rest of my rig. I want to avoid motors that are going to vibrate at these frequencies because they will cause problems on this bracket. Now maybe I want to just avoid the frequencies on the motors. Maybe I want to go back and do some changes to my design to change the resonant frequencies if I really need to run the motor at a certain speed. All depends on the design, but this gives us another tool to help avoid the kind of disaster that we saw on the helicopter. Now, taking a look back at all of the different options that are available to us, we have 3 basic packages of simulation, and depending on what it is you need, you may be able to go with a simple SOLIDWORKS simulation standard to do that linear static study. You may need some of the advanced study types like the frequency that I showed you in Simulation Professional. Some other examples would be the optimization that you saw, thermal studies. Buckling might be really important for any kind of large structure with long skinny parts and compression. event-based motion, drop tests, submodeling, 2D simplification. These are all really powerful tools, and you can talk to your local TriMech representatives about which ones are appropriate for your need. If you need to do the most advanced types of studies, the nonlinear and dynamics, then you might need Simulation Premium. All is available, and we are here to help you, but the idea here is we believe that these tools can both pay for themselves and get you a lot of savings in terms of time, in terms of cost to your design, and can result in better, more effective products for your customers so that we can all make the best possible things that we can make. That is our mission here at TriMech, and we want to help you. I've been Brian Metzger. I hope that this has been informative to everyone, and if anyone has any questions, please reach out to TriMech for help. Thank you very much.